Yeah, the moon, if you gave the moon an Earth's atmosphere, it would hold on to it for about 10,000 years.
Really?
Yeah, before the
Wow.
low gravity and the solar wind.
That's long enough to settle in.
And in fact, you would I forget there's some number, like not an unreasonable amount. Like you'd have to release a small comet's worth of volatiles into the atmosphere every 1,000 years or something like that to replenish the atmosphere because it's small. So
Wow.
the actual volume of atmosphere that you would have to give you one atmosphere level is not that bad. So on the one hand, it's like, yeah, it would be. So it's actually feasible. Well, I mean, to terraform the moon, but I mean, like, what is feasible? Like, it's
Anything
close.
with enough time, energy, money.
Yeah, it's close. I think is the point. So
it's what we in astronomy call an engineering problem.
Yeah, it's an engineering problem. Yeah, I wonder
problem.
though if someone's done the math. Like, would it be harder to terraform the moon or terraform Mars? What would be quicker and require less energy to do?
The moon.
For that matter, terraform Venus.
Yeah. Venus. Well, I mean, I always threaten to push Venus into the sun. So, it's sort of like a countdown here for that to happen. But, yeah, that'd be super cool to terraform. I mean, Venus is like, it's got the right gravity. And that's like the one thing that you can't fix on a planet is the gravity. So you're starting with the one thing that is absolutely necessary. I should say hi to our viewers. I never do that. Hello to Aaron C., Bob Moeller, Gordon Dewis, Ian Farquharon, Jay Alexanderson, Jim Birdsley, Johnny J., Kevin N., Larry Beckham, Larry King, Martin Bradshaw, Nancy Graziano, Nif T., Rich Wilson, this guy, Tom Van Scotter, and Zap Van Zappen. Hey, everybody. Welcome. And of course, people are wondering about SN10. Of course, we'll be talking about SN10 in the show. Larry Beckham says, first priority, stop Venus forming the Earth. Yeah, good call. And in fact, all we have to do to terraform Venus is just learn everything we're doing here on Earth and then just do the opposite to Venus.
Send the Azolla fern.
What is it?
Azolla fern. That wouldn't work though. There's too much toxic stuff on Venus so far.
Well, there are some life forms that are ready to go to Mars right now today. Some cyanobacteria, some lichens. They could. There was a experiment they just pulled off the International Space Station, and it did just fine. Some were punished by the being out in the vacuum of space, but a few were all right.
Wow.
Yeah, it's sort of surprising. Like, you'd think that we would have to go and like genetically modify it and go into very special regions and stuff. But if you just simulate the conditions of Mars, yeah, we already have life that can handle it, which makes this idea of planetary protection all the more important because, our filthy spacecraft can what do you know? Everywhere we go, all we see is more cyanobacteria. That's weird. we see water bears and cyanobacteria everywhere we go across the solar system.
Hopefully we're better at prepping spacecraft than that. I mean, they certainly try hard.
Yeah, no, but you can't get it all. It's like brushing your teeth. You can't
nice analogy. Planetary protection is like brushing your teeth. Just do it already.
Yeah, you got to do it. You're not going to get it all, but it's still important. All right. Let's start. You guys there. There's me. Time for the intro. All right, here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, March 3rd, 2021. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about Starship SN10, launched twice today. An exotic explanation for the most extreme gravitational wave detected ever. Mercury and Saturn almost become one. huge towers at the moon's south pole. I'm assuming some kind of astronomy experiment, and moon cave exploration. Joining me this week on my screen right now, we got Alex Tichy. Hey, Alex.
Hey, Fraser. How you doing?
Good. How's Taiwan?
Love it here.
Yeah?
It's great.
How's the weather? Is it warm there?
What's that?
Is it warm there?
Oh, it's been like mid 70s, mid 80s some days. Yeah, it's real nice.
Oh, that's yeah, we're pretty cold here in Canada still. We got Pam Hoffman. Hey, Pam.
Hey, Fraser. Thanks.
And I'm assuming you're in California, so I'm assuming
Yep.
it's all.
Got cold today, though.
Oh, okay.
For us.
All
For
right.
us.
Yeah. And Brian Coberline. Hey, Brian.
Hey, Fraser. Good to be back again.
And all right, so we're going to get on with the special guest interview in a second. I remembered everybody, right? Yeah, okay. We're going to get on with the special guest interview in a second here. But before we do, I want to give a shout out, as I always do, to our good friends at the Weekly Space Hangout crew. They are our fans, but they are also our executive producers. They consume the show, but they also create the show. And so if you want to be just hands-on, being a important executive producer in the space media landscape, you should join the Weekly Space Hangout crew. Go to wshcrew.space. They'll hook you up with all the various communities and also teach you how to be an executive producer for the show. All right, let's get on with this week's guest. We got Nick Castle. Hey, Nick, welcome to the Weekly Space Hangout.
Thanks. Happy to be here.
So I always ask people, who are you? What do you do?
Well, it turns out I'm a meteoriticist by training. We would call ourselves meteorologists, but the darn weather people got there first. It means I study meteorites. The other thing I do is I'm a mission operator with the CheMin instrument. That's short for Chemistry and Mineralogy, which is on Mars Science Lab. You know, Perseverance's lesser known older sibling.
Right. Well, let's tackle this in two ways. So first on the meteoritology, is that right?
Meteoritics.
Meteoritics. Okay. All right. The meteoritics field. What is like some of the work that you're doing in that area? What are you studying?
So what I'm studying is how a lot of these, so almost every meteorite we have is what we call an igneous rock. This is a rock that formed through a volcanic process. Usually it's we'd call an intrusive igneous rock, so the stuff that formed under the volcano instead of the stuff that erupted out the top. And the question is, how did that stuff form? And what does that tell us about the inside of the planet's mantle? And what does that tell us about planet formation in general? So what I'm looking at is something called oxygen fugacity, which is all sciencey and technical. But really it's just looking at what were some of the fundamental conditions for the system? You know, what can that tell us about the interior of Mars?
Well, I mean, you're talking about specifically about Mars. I mean, what worlds do we have meteorites from at this point?
Well, we have meteorites from anywhere between 12 and 12,000 different worlds, depending upon whether you think every meteorite is from someplace different or if you can group them. A good guess is we've probably got somewhere in the 60-ish number of what we call parent bodies represented in meteorite collections. But there are two that we know for absolutely certain where these meteorites come from. Care to guess which two?
I'm going to guess Mars and Vesta.
Good guesses. It turns out it's Mars and the Moon.
Mars and the Moon. Okay.
I know for sure the Moon because we sent people there to pick up rocks, brought them back, went, hey, this looks familiar. Actually, it turns out before we did that, there were a lot of different meteorites that we thought all came from the Moon with reasonable explanations for why, but it turns out we were dead wrong. Mars is a much more complicated story. We figured that out from inside the meteorites themselves. There's some trapped glass pockets that had little bits of atmosphere preserved, and the atmosphere composition was a great fingerprint that's unique to Mars. Now, Vesta is an interesting case because we've got a really compelling case. The surface of Vesta has the same mineralogy of a meteorite group that we have here called the howardite, eucrite, and diogenite meteorite group. That's a really good spectral link. I would say that's just shy of definitive proof because I want to see isotopic systems. There's enough complications in the HEDs that I want to know, well, is it the main set of things we see or one of the other subsets? So that's almost proven, but
Right.
not quite, in my opinion.
But nothing
minority.
from Venus or Mercury so far.
Nothing from Venus. In fact, we're not sure that Venus ever got hit by a large enough impact to have ejected material out of its planetary gravity well and all the way to Earth's orbit. And that could be why Venus has such a thick atmosphere.
So in other words, the late heavy bombardment was actually good for life on Earth.
Yeah, from what I can tell.
Right. Apart from the death. Okay, so
Details.
Yeah, exactly. And so that's the sort of the one part of your work, and then the other part of your work is working with the Curiosity rover. So how do you interact with the rover?
Well, it turns out I'm what's called a payload uplink downlink lead, which means on any given operations day, I help design what tasks my instrument is going to do that day. Now, there's a whole hierarchy that talks through what's our scientific priorities, what instruments get how much time, power, data volume, all that good stuff. But when we're selected for an activity, people like me sit through and write up the scripts for, okay, this is the commanding we have to do to actually use that instrument. So my instrument is what's called an X-ray diffractometer. And so that's different from the cameras that can get spectroscopy, some of which can reveal about mineralogy, or things like the laser or the alpha-ray particle X-ray spectrometer, APXS, which get elemental compositions. What we get is the mineralogy. And the context there is kind of like if you were baking. If something said, there's eggs in it. Great, you know there's eggs in it. That's information. If you're allergic to them, that's critical information. But doesn't tell you what form those eggs are in. Is it an egg on toast? Is it a cake? Is it something else in between? Like, we don't know. And it turns out that information is really important for geologists. So that's where my instrument comes in. And
so how do you use the instrument? What are you actually scanning? What kinds of samples and such?
So anytime the Curiosity rover does a drill sample, it creates a rock powder. And that can be delivered into my instrument, and that's when I get to analyze it. So we rely heavily on the different imaging teams and APXS to tell us what samples are worth taking, because it takes about a month to do a full drilling campaign from identifying the target, validating you can do it, actually doing it, validating that you did it, delivering it to the instrument, running the instrument, and oftentimes as well, sample analysis at Mars, the SAM instrument, also want some of these samples. And between the two of us, we're both power and data hogs. So we take a lot of time.
Yeah. So I mean, with that amount of time taken to actually perform the full analysis of whatever of the drill site that you're going to do, then there must be a gigantic list of places that you want to scan at each region. And of course, at the same time, Curiosity is on the move. So it's sort of, I can imagine it's like a whole bunch of people battling for the wheel of the car. Whoa, we want to keep driving. No, we want to stay here. Yeah. And this is a continuous debate on every mission. You don't simply have time to use every instrument to its fullest. We try. We maximize what we can get out of it. But if you'd given me my druthers, we would have done a couple hundred samples with CheMin and gotten nowhere. Right. Which means it's really good I'm not the only one in charge. Right. A lander. You would have turned Curiosity into a lander.
Basically.
Yeah. I mean,
so the more you look at an area, there's just so much more fascinating detail. And so there's always this interplay with, keep the big picture in mind, got to move along, but can't miss this. It's really exciting.
So, I mean, like when you're a geologist and you're out in the field and you're standing in some spot, for most of us, we just look around and we see a bunch of rocks. We might be able to see like, okay, there are clearly some kind of layers over there. Maybe there's some kind of sediment over there, while there's some igneous rocks over there and there's some metamorphic pebbles on the beach, whatever. I'm sort of imagining what it's like to look at one of these landing sites. From our eyes, it's even more the same. It's all sort of shades of red rock. How do you sort of distinguish interesting targets?
Well, honestly, most of the time we look for what's different. So if you're seeing kind of the same monotonous stuff all the way along, sure, you might want to sample that every once in a while to make sure that it hasn't changed without you noticing, which it does. and that's exciting too. But you're looking for what was weird. Like one of the places we looked at, there's some big white, possibly vein materials, possibly a depositional environment. That is, a layer of rock that was put down originally, rather than something that happened afterwards. And we weren't sure, so we analyzed it. We did a sample in the weird stuff and right next to it in the normal stuff. It turns out that's one of the places we found an unusual mineral called tritomite. This is the buckskin location, way back, actually, way before I joined the team. And some of the most exciting discoveries were just, hey, that's weird. What caused that? What is that?
I guess, to find surprising minerals in places where you weren't expecting them. What would be something that you're hoping to see, sort of within the realm of possibility? I mean, obviously, it would be great to see a skeleton of a ichthyosaur, on the side of a.
I would love to see a whale skeleton
Sure,
just
that would
sitting
be
on
great,
the ground, like, okay, sci-fi dream come true. Thank you so much.
But, so what is something that would tell a really interesting story? The analogy that I'm sort of thinking of is like, I remember when we watched From the Earth to the Moon, and there's a whole episode where they taught the astronauts how to be geologists. And when they went to the moon, they found the rock that helped really, really solve the case for the formation of the moon. So is there something that you could find on Mars that would sort of be of similar importance?
There are a lot of things that we're looking at that are really changing our view of the geologic history of Mars, that are just, not all these surprises are anticipated. I mean, so there are kind of three major things that motivated us to send the Curiosity rover to Gale Crater in the first place. One of them was called Vera-Rubin Ridge, or Hematite Ridge, before it was more formally named. And that was a place where there's just a really strong iron oxide signature that stuck out from the rest of the landscape. Just a little bit uphill from that was an area that had a strong clay signature. Now, one of the coolest discoveries of the mission is that clays are everywhere in Gale Crater. But this one region, we saw there's extra clays. And it turns out we could back that up once we finally get there. But one of the things that's really exciting for me that we're just arriving at now is there's a transition from a little more normal fluvial sedimentology, so mudstones, which we've been looking at for most of the mission so far, to a sulfate unit. That's a huge climatic change. That's going from normal river geology to here's an evaporite deposit. So what shifted in that? And
Does that mean
story
that it
is something
hotter or colder?
Drier,
yeah,
mostly. And so the question is, what was the context for that? What made it so much drier there? I mean, this is something we see all over the face of Mars. And so having one place where you can really see that in situ is cool. It adds a linchpin towards truly understanding that geology on Mars. So I'm just really excited to see what that transition looks like as we actually get to it in detail.
Yeah.
This is like on the Earth. I'm sorry.
It's okay. There's a citizen science project called Teaching Mars Rovers How to Classify Martian Terrain. So you might be getting help from the public with that. I think it's brand new. I don't know. Jeff will talk about it more on Friday during our show.
Oh, cool. Okay.
I'll have to tune in for that.
So now, people are asking in the chat about Perseverance. Of course, you're involved in Curiosity, and so you're not on the Perseverance team. So is there? I mean, a lot of minerals are biological based. So is there some kind of evidence that you could find through your line of work that would help give some kind of evidence of past life on Mars?
Absolutely. I mean, exactly what that evidence is, I'm frankly not enough of an astrobiologist to tell you for sure. But there are a number of different minerals that more commonly form through biologic activity, through life. And if we saw significant deposits of that, then we'd have compelling evidence for life just from mineralogy. Now, a lot of these would also be things that you might be able to capture with a camera, or that you could get through elemental compositions. And so we're hoping to see those things with the Perseverance rover. I mean, one of the things that Curiosity has as a real strength that Perseverance doesn't is the ability to look at definitive mineralogy. Perseverance can infer some of the mineralogy and use spectroscopic techniques to try and pin down what some of the minerals are, but it can't quite get the same mineralogical context.
Right. I'm sort of imagining, like limestone or something, right? The White Cliffs of Dover. And even here, like where I live, we've got a lot of shale from some ancient seabed. And so wherever the deposits are showing you just tear them apart and they're filled with fossils, just tons of little marine animals and the occasional bigger. We've had a couple of
Yeah, I
dinosaurs
would
found.
absolutely love it if we found a coal seam on Mars, because then I'd be sitting back going, yep, okay, life and lots of it.
Right. Yeah, because coal would mean trees, and that would be
Absolutely.
that. Yeah, yeah.
Yep,
But so far, no. No coal so far.
not so far.
Yeah, or oil. But maybe that's good, because then, we don't want to sort of send people to go and searching for oil on Mars. So now you study meteorites. You also study rocks on Mars. Have you had an opportunity to do both? Have you been able to study a meteorite on Mars? I know they have fallen around. They've been seen.
So most of the meteorites that we've seen on Mars's surface are, for me, the wrong kind of meteorites. They're iron meteorites. So I study Martian meteorites to try to understand the origin and history of Mars. But every now and then, on the surface of Mars, we see a chunk of essentially iron that's staying on the surface, and that's definitely a meteorite.
Yeah.
Unfortunately, I just don't happen to study that. So it'd be cool, but unfortunately, I don't know that field.
Right, but so far, like a nice stony meteorite hasn't been seen sitting on the surface of Mars.
Not that I'm aware of, and not that we could really prove for sure.
How's the rover doing? How did you sort of imagine the future unfolding? I mean, it's still going strong, right?
Yep, still going quite strong. So the power supply is slowly cooling off. From what I understand, and I'm not a nuclear engineer, so please don't ask me too many details. But from what I understand, it's actually some of the physical structure of the RTG that'll eventually break down. It's not about the radioisotope source itself. I mean, that'll stay hot for a good long time, but we won't be able to make power from it once the power plant breaks. But it slowly decays at a predictable rate. That is the engineered power source. And eventually that will limit what we can do to the rover, and eventually to a point where we can no longer move it, and it'll become a permanent station. That's just because we won't be able to, on a reasonable timescale, store up enough power to move productively.
Right. I've got one kind of out there question for you, which is, we know of a couple of interstellar objects that have been seen in the solar system. Oumuamua, we know of Borisov. Has there been any inkling of a meteorite that's been extrasolar in origin?
I don't know of one. I would love to find one. But usually what we talk about with, once you studied it isotopically, it could be very obvious. What we've seen that's from out of the solar system in meteorites are pre-solar grains, is what we talk about with them. And these are things that have isotopic signatures wildly different from anything else we see in the solar system, to the point that there isn't a rational way to explain how this came about within our solar system.
Right.
But these are essentially small dust particles captured within chondrites.
And so, like, clearly there was a universe before our solar system, according both to the other observations, but also these meteorites. But I wonder. I mean, it's such an interesting question to, like, all of the assumptions that we have about just the way the solar system formed, how it all came together, just comes from all of these meteorites, which are very similar in age and a lot of the story that they tell. It would be just amazing. It would be like getting a book in another language.
Yeah.
That's
one
it.
of the things,
Yeah.
I mean, one of the reasons why I got into planetary geology is because as a geologist, I kept asking annoying questions of my, particularly my geomorph professors. Like, here's how a river valley develops. Great. How does that change if it's a third of the gravity and a tenth the atmospheric pressure? Nick, quit asking about Mars. Every time we get a different example of how nature works, we learn just wilds amount more. So your analogy of it's a book in a different language is really apt. It teaches you a lot more about just what was an assumption, what's a fundamental process, and kind of lets you pull those things apart.
Right.
So I would love to see rocks around another star.
There was a NIAC grant that was just awarded, just announced a couple of days ago, that to examine a interstellar object, a sample return mission from like an Oumuamua or Borisov. So it would actually chase down one of these and then return a sample back to Earth, like Hayabusa 2 or something like that. So who knows? Maybe within our lifetimes, we'll get our hands on a chunk of rock that came from another star system, which would be incredible.
Please. I would love it if we did that. I'd love it even more if Arthur C. Clarke was right and it's Rama. But,
Well, not specifically Oumuamua, the next one that passes through the solar system, we gotta jump on it. But, well, Nick, thank you so much for taking the time to chat with us today. If people want to follow what you're working on, and even I think there's a way they can get involved and learn from you, right?
Yeah, so I'll actually be teaching a public interest science course. It's called How to Live on Mars and Not Die. And the course is about, what is it that makes Mars so hard? And explaining some of the science behind that and presenting these things not as reasons why we shouldn't, but what are the challenges we need to overcome? So that people can go from kind of that Star Trek, we flew over to the place after fueling up the Enterprise, beamed down the surface, we're there, right?
Yeah.
And be a little more sophisticated about, well, what's so hard about Mars? So
that sounds great.
People are welcome to sign up for that.
And so if people want to find that, where should they go?
It's on Eventbrite. Just look for How to Live on Mars and Not Die.
All right. Awesome. Well, Nick, thank you so much for taking the time to chat with us today, and good luck in your search for interesting meteorites. And I hope you do find that coal on Mars.
Well, thank you so much for having me today.
All right. See you later. All right, let's move on to the news of the week. Pam, you're on my screen.
Thanks, Fraser. Appreciate
you go first.
That. Yeah, and I really like to talk to people about stuff they can do. That's why I mentioned the project. But for astronomy purposes, the excitement this month starting off is in the east before sunrise. There's 3 planets. They're really low in the sky, though. Of course, Mars is still really bright and high in the sky, sort of southish, and it's going to kind of settle into the west. Vesta is a really cool object you can see, and it's 6.3 magnitude, easily seen with binoculars, and that'll be in the tail of Leo. And I think it's finally rising at sunset now, so it's going to be like I was saying before, easier and easier to take a look at. Very specifically, though, on March the 5th, and this is the really cool thing, Mercury and Saturn are in conjunction. They're nearly merged. They're saying this is also before sunrise in the east. It's very low. I'm so sorry, Fraser. You're not going to be able to see it where you are.
I know. So then hold on. So how close? Like in the same telescope point, like the same thing that we saw with Saturn and Jupiter last year, like that kind of close?
So I haven't seen any numbers on that, but I mean, if they're saying they're nearly merged, I mean that's exactly what happened last December with Jupiter and Saturn. So. Yeah, if you've got a really low horizon in the east, folks, get up before the sun rises and take a look. I think that'd be wonderful. I have trees, unfortunately.
Yeah, it would be great to see somebody actually take a picture and resolve the two together.
That would be fantastic.
That'd be terrific. Yeah.
And we've got last quarter moon. That's something you see in the evening. It's pretty much directly overhead and sets at I'm sorry, that's the last quarter moon is at sunrise. You see it overhead, and then it sets at midday. March the 6th, Mercury is at its greatest western elongation. That's the time it gets highest in the sky, where you can see it. Still not going to happen for you, Fraser. Sorry.
It's all right. Yeah.
And then the 8th, and here we go again with Pluto, which is a little too dim to actually see, but the moon is really small. That's going to be a good way to find it, though. I really like to have
you can find Pluto with a telescope, with a like an 8-inch or larger telescope.
You need the actual right ascension and declination for that, right?
Yes. Yeah. But if you've got a powerful enough, even backyard telescope, you can see Pluto. We brought them into the virtual star party in the past. So,
Oh, very cool. I'll have to
Yeah.
see that sometime.
Yeah.
The 9th is Saturn and the Moon are in conjunction. The 10th, Mercury, Jupiter, and Neptune. Again, Neptune not visible with, you need application for that. They're in conjunction. That's again in the east before sunrise. Lots of stuff happening in the east before sunrise, like I said. But it is easier to see Mercury and Jupiter. So, and the moon is still small enough. I know when it gets really bright, it's going to be hard to see some of those really dim objects, but that's going to be a good time. That's the 10th. The 12th, Venus, Neptune, and the moon are in conjunction. And I could go on. I mean, we've got daylight savings time, and we've got,
Is that this month? Oh,
the 14th. Yeah, spring ahead.
right.
If you do that in your part of the world, not everywhere does. But yeah, so it's going to be weird again for a little while.
Yeah, I like the spring forward. I don't mind that.
Yeah, I hear you. On the 19th, Mars and the moon are in conjunction. That's high in the sky. The 20th is the equinox.
Wow, it's a busy month.
Yes, it's very busy. I mean, contrast with how slow it was for a lot of February. It's like, oh my God. So I put this list in the chat again because there's a lot more.
Awesome.
So yeah. And next meteor shower, you asked me last time, it is not until April. So we got to wait.
And we've got some pretty good aurora activity as well. We had,
cool.
Yeah, there was some activity here for the north anyway in the last about 2 days ago, and
wow.
And so I think as we move into as we move out of solar minimum and start moving our way towards solar maximum, we're going to see more and more activity on the sun, more sunspots, more aurora activity. And
so those are actually. It's basically a causal relationship, right?
Yeah, right. So when you have
I don't actually know.
Yeah, when you have the sunspots, you have the magnetic field. The dark spots on the sun are where the magnetic field lines are piercing the surface of the sun. And then when the magnetic fields on the sun sort of reform themselves, you get this snap, and it throws out this material into space that hits the Earth and interacts with the atmosphere and
basically
and
comes right into the
and goes towards is attracted to the poles of the planet, and you see the aurora activity. Yeah, and so it's a perfect as we get this activity more, and so I always tell people, like, even if you're in lower latitudes, you can still see auroras when they're very strong.
I saw one in Conneaut, Ohio, and that is not in northern Ohio. It's like central-ish.
Yeah. I think you're out where you are because you're in like Southern California, right?
Yep.
Yeah.
We're closer to the pole. No.
Yeah.
I mean the equator. Sorry,
but,
not happening.
But people who are in the northern half of the United States can definitely see the occasional aurora. Usually 1 or 2 a year, but you need to have the aurora alert tell you when it's time to go. And so, like, for us in Canada, we could see maybe 10 shots at it, while people in the northern US get like maybe 2 shots at it. But still, but when it works, and it's amazing. And you can even take pictures of it and see, aurora activity on the northern horizon. So this is just that reminder now. Get yourself some kind of aurora alert system. People always ask me for a recommendation. I don't have one. But there are apps that'll tell you when there are aurora alerts happening.
That's cool. Yeah. What we saw in Conneaut, Ohio wasn't that exciting and interesting. However, it was like I could see it.
Yeah.
I was blown away at how far south we were there, and we could still see something.
Yeah, absolutely. Wonderful. Thank you so much, Pam.
Yep.
All right, Alex, what do you got for us?
Oh, yeah. So this was a very interesting paper that came out just a couple of days ago. And the lead author, I think, is an undergraduate student at Harvard. So very impressive. Sephora Ruppert was her name. Put out this paper with some engineers and other folks at the Center for Astrophysics at Harvard about building towers on the moon. Kilometers high, 10, 15, 20 kilometers high.
Easy, because gravity's so low.
That's right. Yeah, gravity's low. No atmosphere, of course, and pretty limited seismic activity on the moon as well. So sorry, I've got a baby crying out the window. But so it's sort of interesting, just kind of thinking through this problem. How would you build a tower on the moon? Well, they propose
that might be the second question I would ask.
Yeah. So why, right? Shall we start with why? Why is a good question. Of course, we're interested these days in the south pole of the moon in particular. The thinking is that there's lots of frozen water, ice, down at the south pole, especially in these bottoms of these craters that basically never get sunlight, right? They're sunk down in, and we're at the south pole, so the way that the sun hits us, I don't know why I've got so much sound on the street all of a sudden. Good Lord.
Because you're shooting video. That's why.
Yeah, I know. It's been quiet the entire time. Sorry about that. We got a lot of scooters here in Taipei. I think that's what it was. But yeah, lots of ice in the craters at the South Pole especially. And this is some place that NASA is particularly interested in sending humans there. Water, ice, of course, interesting, good for us, not just because of consumables for drinking water and all that, but you could actually make rocket fuel. You split up the water into hydrogen, oxygen, and make fuel that way. So it's a very efficient way to source your materials. The problem, of course, is that you're sitting down in perpetual darkness, and so the idea behind building these towers was that you could sort of build up high enough that you could put solar panels on these towers and basically replicate what they call the peaks of eternal light. Right. Very nearby these craters, you have these mountains that are practically always in sunlight, not 100% of the time, but they receive a lot of the sunlight down there. So the thinking was that you could build a tower that would do the same thing. The question in my mind is, well, why don't we just build a nuclear power plant down there? I think it might be a little bit easier than building kilometers high towers. But nevertheless, this is sort of an interesting.
All right. So how? Now I'm intrigued. Tell me how.
Well, so they want to use, they say, sourcing steel from the earth is prohibitively expensive, of course. So you can make concrete out of the lunar regolith. And of course, they don't go into how you would do that, but it seems like
it's pretty well understood at this point.
Conceivably possible. And so they run the numbers and said, based on the low gravity, based on no atmosphere, low seismic activity on the moon, you can build these towers up to 10, 15, 20 kilometers high. Now, that's an enormous engineering challenge. We have not built anything close to that high on the surface of the Earth. And so talking about how you would build such a thing on the moon, might sound far-fetched, but I always really kind of like these ideas when people say, I have a couple of friends recently put out a paper about having basically like a space elevator of sorts attached to the moon. We should be thinking about these problems, even though it seems fairly far-fetched, 10 or 100 years in the future, whenever these sorts of things might be. It's interesting to kind of be teasing out these ideas now.
Yeah, I'm all for it. I was just Googling the tallest radio tower is 650 meters. The Warsaw. Oh, no, wait. The Burj Khalifa is now 829 meters.
Yeah, Burj Khalifa is pretty.
But I wonder if aren't there radio towers that are taller than the Burj Khalifa? Anyway, so then I guess you can multiply that by 6. So I don't know how you get a 20-kilometer tower though on the moon if you took.
Yeah, I mean it's the paper is mostly just kind of engineering equations. What's minimum thickness that the concrete can be at the very top.
I mean, there's no atmosphere, there's no earthquakes, so
it's a lot wider the base. How thick does it have to be at the base? How hollow is it? These kinds of things. So it's mostly an engineering paper, and very coarse on the details, as you might imagine. But it's kind of a fun read.
That's really cool.
It was like satellites would be easier to build on the moon and launch to do the same work.
For you mean like beaming energy back to the you could do. I mean, if it's at the South Pole, now you can't have sort of lunar stationary orbits the way you might, when we have to think about lunar stationary.
Okay.
You want to be at the equator, so being at I guess you could have the thought occurred to me too, right? And then you'd have to have sort of a suite of these things sort of on this highly elliptical, I think like the Soviet Union pioneered these really highly elliptical orbits for the communication satellites, I guess, where they spend a lot of time over Russia, right? So you could do something like that where it spends most of its time over the pole and sort of beam that sort of, and own engineering challenges associated with that, of course.
Yeah.
I think a nuclear power plant is probably the most.
Well, the idea that I had heard is a cable. So
Yeah,
you build
cable would-
solar panels on one of those mountains, and you just run a cable down to your.
Right, that occurred to me too. Yeah.
Yeah. Awesome.
Maybe a little easier than kilometers.
Such a long tower, a tower that is taller than has ever been built on Earth,
Right.
even when you consider the gravity. Yeah, maybe.
Yep.
No, hey, I love their enthusiasm. More things built on the moon, please. All right, Brian.
So this is some research looking at a gravitational wave merger event that happened back in 2019. It was GW 190521, which means it occurred on May 21st in 2019. And it was the largest merger event that we've detected so far. So when you run it through the models, it was a 66 solar mass black hole merging with an 85 solar mass black hole to create a 142 solar mass black hole. And it had a lot of news at the time because it was the first gravitational wave detection of what we would call an intermediate mass black hole, which is something bigger than a star, but not a supermassive. And that's anything over 100. They would say, okay, fine, that's an intermediate mass black hole. So this was the first of that had a merger event that had a black hole end result greater than 100 solar masses. But the more you look at it, the more odd it is. And the really odd thing about it is that these were two very large black holes that had merged. And the problem is they're both kind of stellar mass black holes, but they're too big to be stellar mass black holes.
Right. I remember that they're in this sort of desert of black hole formation that when a star explodes, you shouldn't be able to get a remnant that's that size. You can get a smaller remnant or a heavier remnant, but you can't get a remnant that is in that middle zone.
Right. So the idea is that from a single star, you really can't get more than 65 solar masses. And anything larger than that would be a merger. And those would probably be much larger. If you have two, big stars that would typically merge, they would be in the 90s or close to 100, kind of like the end result of this. But this one, particularly the 85 solar mass, it's kind of small for a merger, but it's too big for a single star. And so, one of the questions is, how do you make a star like this? And people have come up with, maybe you had like a small multi-star system that gradually merged over time to create this. But an alternative that this new work looks at actually draws upon research from the 1930s. And there was a guy by the name of Alexandru Proca that looked at how quantum fields could interact with gravity. So when we think of like collapsed stars, we think of, okay, there's a black hole, but there's also white dwarfs and neutron stars. And those are stable because of a quantum interaction. Matter is either electrons for a white dwarf, it's the pressure of the electrons, because electrons are fermions. They're a type of particle that won't occupy the same state. And so because when gravity tries to squeeze them, the electrons push back, and that gives them a balance point. Neutrons, although they're made up of quarks, are also fermions. So that same fermion pressure, what they call degenerate pressure, prevents it from collapsing. And that's how you can have, a white dwarf and a neutron star. But of course, if you have too much mass, it collapses into a black hole. So there's this idea of what happens, not if you have fermions, so electrons, neutrons, quarks, but bosons, which would be like gluons and photons and
like light. Light is a boson, right?
Light is a boson, right? So it has to do with a thing called quantum spin, that basically fermions are half integer and bosons are whole integer. So this guy by the name of Proca looked at what would happen if you had a field of bosons in a gravitational field. And it turns out that we know a lot about bosons now. We didn't know much about them then. But we know that, for example, bosons can collapse into a single state. So you can get something called a Bose-Einstein condensate. So if you have, super cool a certain type of atom, and they'll cool down into this single quantum state. So you would think gravity would just crush it into oblivion and become a black hole. But it turns out that the spin, the quantum character of bosons interacts with the gravitational field, because quantum mechanically, gravitons, if they exist, would also be bosons. So there's this complex interaction that would prevent a mass of bosons from collapsing on itself. So you would get a similar type of object. And when Proca was looking at this, he was just looking at the interactions, but later people would calculate this and say, if you have the right type of boson, you could actually have something that's above the mass of a neutron star and still not collapse into a black hole.
Because it's sort of like acting like a big crystal, like a big boson crystal.
Right. So they call this thing a Proca star.
Wow.
But it's just a mass of bosons that doesn't collapse into a black hole.
How would you get it in the first place?
So this is where people started speculating. They speculated early on to say this can't be a black hole, and then we found, yeah, these are black holes.
Right.
And now they're kind of coming back, because all of the regular matter that we have, all of the electrons, protons, neutrons, quarks, they're all fermions. And bosons are gauge bosons. They're fields that exert the forces between them. We don't have boson stuff, boson matter. Yes, photons, but like an electron, but a boson. We don't have that kind of thing.
Right.
But that has been proposed for dark matter. That dark matter might be a type of boson matter that is similar to the way regular matter is fermion matter. So if you have these dark matter particles that are bosons, they could gravitationally collapse. They could form a Proca star.
So this sort of feeds into another piece of research that got released, I think this week or last week. I don't know if you worked on it at all, but this idea that dark matter in the early universe could just form directly into black holes.
Right.
So this is kind of a
parallel track.
I mean, does this kind of mean that supermassive black holes might be these stars instead, formed out of dark matter? And that
there are people who have proposed that at least some supermassive black holes could be Proca stars. And in fact, there is a paper that I cited in the article that looks at how would it look if you had something like the Event Horizon Telescope. And the difference is that because it's actual matter, if it doesn't cross the event horizon, that means that you can have strong magnetic fields. So basically, when a black hole collapses, the magnetic fields can be in the material around it, but not at the black hole, not past the event horizon. And so what that means is that if you had a strong magnetic field in a Proca star, that would change the way light lenses around it. So if you could use an event horizon telescope, kind of like M87, but did it with a Proca star, it would look different. It would be a different spectrum.
But the fact that they did image M87 means that M87 is a black hole and not a Proca star. I mean that.
Right. So we know that M87 is a black hole. We don't know if all supermassive black holes are black holes.
Right.
They could be Proca stars.
And so
it's very hypothetical.
Right. And so the way you would look at it and the way the event horizon would look would be different than the way the event horizon of a regular old boring black hole would be. Okay.
Right. And also the mergers would be different. And that's where this paper comes in, because when you get these kind of gravitational wave signals, there's so much noise, you have to match it to a model. So you make some assumptions about the model and see how well the data fits. And the standard way is to do it to a black hole. You can do it to the Proca star model. What if it is a merger of two Proca stars? This also matches the data. And they're about equal. When this research group did it, they matched it, and because it puts a constraint on the type of boson, basically the mass of the boson, they used it to calculate what the hypothetical mass would be. And it was tiny, but it's not zero.
Right. I mean, I think the source of why this is so interesting is because when you start out and say, like, it's not easy to get the source objects colliding with each other. That's the problem, is that to have a black hole that's 85 times the mass of the sun and have a black hole that's 65 times the mass of the sun merging together, those objects shouldn't easily exist. Obviously, if there were more mergers earlier, you could build up to that, but then that you have to tell a very complicated story to do that.
Yeah, there was another work that looked at trying to get an 85 solar mass black hole would require 3 stages. Like the most likely outcome was a pair of mergers, another pair of mergers, and then a third pair of mergers.
Yeah. And so then you could say, well, so if you've got such a weird origination of this merger, then maybe it is time to examine one of these other alternative ideas.
Exactly.
Yeah.
Exactly.
What do you think? What does your gut tell you? Are black holes made of dark matter and merging together in boson states?
I lean towards the traditional black hole model because we know so much more about that. What I find interesting about studies like this is that they're not trying to be hyped. They're just saying, here's a hypothetical thing, what happens? And what they get is, well, this is consistent with the data. It doesn't prove that's what it is, but it proves that maybe we should pay attention to some of these alternatives, given that we don't know what dark matter is at all, and we know it isn't any of the regular matter that we see.
Yeah.
It can't be neutrinos. It can't be part of the fundamental particles. It has to be something else. So either our understanding of gravity is really wrong, or there is something exotic out there, whether they're these bosons or axions or something, sterile neutrinos. You start looking for crazy ideas because we've gone long enough where the obvious answers don't work.
Yeah.
So these alternatives are getting less crazy.
Yeah, I think that's great. I think there's you got to have this tension between people willing to consider crazy ideas and also, fine-tuning the well-worn tracks. So you both want to, search for the Higgs boson because even though you know it for sure it's going to be there, but at the same time go after some of these other interesting ideas. Very cool. Thanks, Brian.
Yeah.
All right, so before we wrap things up, I just want to give a quick mention. Of course, if you were watching YouTube, Twitter, television today, SpaceX attempted to launch and land SN10, and they were successful. So this is the Starship prototype number 10, launched from Boca Chica. It had a launch abort, and then they had to wait another hour or so before they tried again. Right on time on the second attempt, the thing took off, just like as we saw before. The lesson learned this time around, Elon Musk had said, was that they were gonna ignite all 3 engines at the same time and then turn the ones off that they no longer needed. So the thing flew to 8 kilometers altitude, fell back to the Earth, and then at the right moment, kicked the bottom over, landed beautifully in a giant cloud of smoke, and it just sat there, clearly leaning. It wasn't, it hit hard. It still hit pretty hard, and it looked like it kind of bounced a bit when it actually hit the surface. But when the smoke cleared, it had a bit of a lean to it, and we're like, well, that's good enough. It happened, and then if you sort of leave the video running, a few minutes later, it just detonated, and so I guess it flew a second time. So this is the first time that a SN prototype has flown twice. So they definitely proved the that the kick maneuver works. The thing landed mostly safely. Clearly, it's a hard landing. I'm sure they'll work that out. But it was beautiful. It was beautiful to watch. I'm sure do a search. You'll be able to watch the whole thing from many different people, many different perspectives. Congratulations to everybody at the SpaceX team for pulling this crazy maneuver off. Now we look forward to SN11. You're up. 12. You're next. So yeah, I know it's going to be.
That's how numbers work.
yeah. Well, like SN10 got to watch SN9 detonate beside it, so I think this is what could happen to if you sort of stand right beside and watch your brother detonate.
As long as they get past 17, I want them to keep going.
Yeah, no, I'm sure they it's a straight up assembly line at this point. There are pre-exploded rockets being built at a high speed at this point. So yeah.
That's great. It's very exciting.
Yeah, it was exciting, and I'm sure people are like, the mainstream media is going to be calling this a failure, but it was a tremendous success. It was wonderful, and this is how you learn: iterate.
And what amazes me is that other rockets have had to shut down completely and do all this analysis, and a year later they're finally back up. For some reason, Musk is getting around all that and just boom, launching again.
Yep. Yeah, exactly.
Amazing. I was so shocked. I was like, wait, they're launching again already?
So John Suffolk saying in the chat that the landing legs didn't deploy. So but the landing legs for this are these tiny little, I'm sure they're gigantic, but they're these little legs that fold out from inside the actual main body of the rocket. So they don't sort of come down in the way that they work with the Falcons. So, but anyway, it was exciting. I hope if you haven't had a chance to watch it, you should definitely watch it. The actual landing was really impressive, kind of really amazing, and the camera work was great because they just they had this great shot of it just coming straight towards you. But better luck next time. Keep it going, SpaceX. We're watching. All right, Pam, you're on my screen right now. Why don't you tell people what you're working on and where people can find out more?
So first up, I'm going to talk about my book, and that's available on Amazon. Continually, it's always there. And I have copies too. If somebody wants a signed copy, absolutely get a hold of me and we will get you set up. And then we've got our Friday night show. That's really been fun. We've had guests. We talk about, right now we're talking about citizen science. That's Friday at 9 p.m. And you find us anywhere that Everyday Spacer has a channel. Like we have a YouTube channel going. There's Facebook. And that's 9 p.m. Pacific time and midnight Eastern time and so on. The next one is, like I said, we're gonna be talking about how regular folks can help out with teaching Mars rovers how to classify Martian terrain, and that's a project on Zooniverse. And I think it's kind of new, but Jeff's doing the research on that. He's my partner. He's the one that I do the show with on Fridays and ask us questions, and we'll see if we can help you out.
Brian, what are you working on?
I'm working on a couple of articles. I haven't formally decided which one I'm going to do first, but yeah, you'll find it on Universe today within the next couple of days, and then you can also find stuff on my website, which is briancoverline.com.
Excellent. And Alex?
Yeah, I think I've mentioned it before, but what I'm really interested in right now is studying these planetary systems with multiple moons, exoplanetary systems, of course, looking at exomoons. That's my bread and butter. What kind of observational signatures would these planets have if they have multiple moons, and how easy or how difficult will that be to detect? And people can follow me on Twitter if they're interested in hearing whatever I have to say at the moment, at Alex Tichy.
Perfect. All right, awesome. So the NASA's NIAC award was just sent out in the last week. So 12 new awards for some really cool ideas. So I am in the process of queuing up as many of them as I can as guests on my on my YouTube channel. So we're going to be talking about sintering lunar regolith and chasing interstellar objects and all kinds of really cool ideas. So hopefully over the next couple of weeks, you'll see a ton of these interviews come up. Next week, we've got David Kipping, which is going to be great. Have you ever talked to him, Alex? He's a great guy. You should meet him.
Yeah, a couple times.
Yeah, all right. Okay, I'm going to put everybody back up on the screen. There we all are. Okay, so thank you everybody for watching us tonight. Thanks to all of our moderators in the chat. Thanks especially to Nancy Graziano for keeping us all organized. We couldn't do this without you, seriously. Thanks to everybody. I don't know if people are watching us on Twitch as well, so thanks to you too. We see you. And our special guest. Until next week, we'll see you then.
Good night.
If I might stop